everybody, to our final lecture of Unit 1. This kind of builds on the last lecture with the celestial sphere, and we're going to take a look at physical diameter and angular diameter, and just kind of see how angles are used in general in astronomy. We'll talk a little bit about how physical and angular diameter could be calculated. There's a relationship between size and distance, which should be kind of common sense, but for some reason it seems like if it's written out and kind of put in just a formal question, kids sometimes get tricked up with it. I want to make sure we're smoothed out with all that. And again, we'll look at how that declination and right ascension can get busted up into angles and degrees and these little guys called arc minutes and arc seconds. So away we go. Just to review quickly, this should look familiar, right? I mean, it's a basic kind of skeleton of a celestial sphere, and you've got the lines of declination and right ascension, which again, they run like latitude and longitude. And when I was a youngster, the way I kept them straight was I used to think, all right, latitude, I would abbreviate latitude LAT, that's 3 letters. Declination, I'd abbreviate that DEC, that's 3 letters. So latitude and declination are going to be the same. And they're going to measure north and south of the celestial equator, which really means they run east and west. So like declination, 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 or they're like parallels or your lines of latitude on a globe. Right ascension, it's going to be like your longitude. Then it starts at the vernal equinox. We'll look a lot more at the equinoxes and solstices in Unit 2, but that's just sort of our quick review for the old celestial sphere, that pretend shell around the Earth that gives us a good view of where things would be at. It's kind of like a sky map, if you will. So it turns out that the ancients were fantastic at detailed records and very skilled mathematicians, and a lot of the systems that they use to chart star locations in the sky are still used today. And you can go back thousands of years and some of this stuff is still accurate. And you may be asking yourself, but Cash, the universe is ever expanding. How on earth could those things still be in the same locations? Well, I mean, there may be minuscule movements, but again, keep in mind, those stars are so far away that it just takes so long to see some sort of a measurable change here at Earth. We just haven't really experienced that yet. You might remember way back when I showed you that picture, though, of 100,000 years from now, what the Big Dipper will look like. Over long periods of time, I would say much longer than an average human life expectancy, you would see some changes. But their records are still pretty darn accurate and very, very impressive with, just the tools and the unaided eye that they had to use to view the night sky. So when we're looking at the night sky, we can use angles to talk about locations, and we can use angles to talk about distances, and we can use angles to talk about sizes. So just before I get into this here with you, a lot of times if we're out viewing stars by my house or something, I might say, well, look up about 45 degrees. And what I mean by that is if you were to look straight up at your zenith, that would be like looking up at 90 degrees. If you were to look just straight out onto the horizon, which a lot of trees would be in your way at my house, but that would be 0 degrees. And if I kind of split where straight up to the horizon is, that's about 45 degrees. It gives you kind of an idea where to look at in space. So there's a thing called an arc angle, and that's basically a fancy way of just saying an angle in space. And here, if you look at the viewer checking out the pointer stars of the Big Dipper, which we've discussed quite a bit, that's going to help you find Polaris. We see that there are 2 imaginary lines from each of those stars back to the observer. And if we measured that opening, that would be our arc angle. So a little bit of review with degrees and eventually into angles. If we talk about a full circle, or full rotation, which for Earth, that 360-degree rotation is what we refer to as a day. That's 360 degrees. You travel 360 degrees in a day of rotation, and then you could say another 360 degrees of revolution in a year. But we'll look more at that in Unit 2. If I talk about a right angle, that's going to be your 90-degree angle, which again would be from horizon to zenith, or straight up above you to out on the horizon. And that's kind of our intro to working with angles. So one of the ways that you could use angles is to talk about the distance from an object to an object, star A to star B, or the top pointer star to the bottom pointer star. You could use angles to talk about that distance from star X to star Y, or Mars to the moon, or whatever. Another way that you can use angles is to talk about the size of that object. So here we see the moon. And in the night sky, the moon takes up about a half a degree of space. So that gives you kind of a little bit of scale, or some context, a starting point for how much something in the night sky would actually occupy. Full moon is going to be a half a degree of space. So when we talk about that, apparent size, that's just going to be how large it appears. And again, the moon would be a half degree of space. So there's these terms when we talk about how much space something's taking up in the night sky. Like the moon is a half a degree of space. We could say that that's its angular diameter, or we could say it's its angular size. Those terms are interchangeable. They mean the same thing. You're basically just talking about, if I use angles to measure diameter, from surface to surface or edge to edge of a circle, or if we just talk about the angular size, same thing. So diameter, again, that's going to be from surface to surface, or from edge to edge. So like if I'm looking at the moon, if I were to measure from surface to surface, or edge to edge, basically across that circle, that would be my diameter. We got a fancy term we can use to describe how far something is across, and it's subtens. So if you wanted to dazzle your friends with your newfound impressive vocabulary, you could say, the angular diameter of the moon, it subtends 1/2 degree in the night sky. What's all that jargon boil down to? The moon's a half a degree across in the night sky. But subtens is a word that you should be familiar with, because it'll pop up from time to time. So if we're looking at the size of the moon in the sky, and we're saying it's a half a degree, what if other things were our moon? Or maybe another way of saying that is, what if our moon was the size of other things? Let's take a peek here. So there's the moon. That represents 1/2 a degree. Let's swap it out for some planets and see what they would look like. Here, we've got Mars. So if Mars, about third the size of Earth, was the distance, 250,000 miles from Earth, that's what it would look like. Venus, larger than Mars, not surprising. Impressive. Jump to the outer planets there, right? That's Neptune. Uranus, looking very similar to Neptune there. Holy smokes! Jupiter, look at the great red spot there. Thing's a monster. How impressive would that be? Can't imagine what our tides would be like. Ah, Saturn with its impressive ring system. See how they look solid? Again, that's just actually little bits of ice and rock and small debris, but there's enough of it where it gives it almost like a solid appearance. Looks like you could walk on it or something, but that's not the case. Okay, so those would obviously subtend much larger angular diameters or angular sizes in the night sky. But we got the moon, and we'll spend a whole unit when we wrap up the class looking at eclipses and moon phases and all that good stuff. So how the heck do you measure all this stuff in the night sky? Well, you could use a protractor, or your cell phone app may have something, or you could use your hand. If you look at this picture here I got from our text, it gives you some little tricks of the trade. If you were to look at the average distance, I understand people's hand sizes are different, but this gets you a pretty decent approximate. Like the width or the diameter of your index finger is about 1.5 degrees. If you have like a closed kind of like karate chop hand like we see here, from your pinky edge to thumb, that represents about 8 degrees of space. If you look at on the right there, your index finger, if you kind of bend it a little bit there, you can kind of see that distance of your first pointer to knuckle, or those of you who have taken forensics, if we were talking about your distal and proximal ends, but we're not. This first chunk is about 2 degrees, that middle chunk of your index finger is about 3, and that longest run there is about 6 degrees. So that's something that you could use to estimate distances in the night sky. Here's another little picture that I found online that I thought was kind of interesting. You've got, basically your pinky is 1 degree, your fist is 10. You've got your 3 fingers, from your middle to your index is about 5 degrees. And if you're just going like, the devil horns, it's about 15 degrees. And if you're going to hang loose, it's about 25. So there's pretty easy ways there that you could use to estimate distances in the night sky. And again, there's 2 ways you could use that, right? I mean, if you were talking about from this location to this location, or if you're talking about the size that something is in the night sky, angles work well. So, all right, push yourself back from the screen a little bit. Close one eye and hold up your index finger, which you might remember your index finger is going to be about 1 degree and a half of space. We know that the moon is about 0.5 degree of space. So which of these dots do you think is closest to what the full moon would look like in the night sky? Surprisingly, it's actually A. It seems like a lot of times kids will think about the full moon as being this huge object in the night sky, but then after we talk about the degrees and stuff, they look up and they're kind of surprised as to relatively how small it is compared to what their memories thought it was. So can we get further than degrees? You betcha. Again, keep in mind we've got 360 degrees in a rotation. All right, a full circle. Okay, well that would be a day for the Earth. If we've got one full rotation, one 360 degree trip, that's going to be 1 day. So days can get broken down into hours, and hours can get broken down into minutes, and minutes can get broken down into seconds. So if you take a peek at this, a degree, it's kind of like a hour, in that it can get broken down into 60 arc minutes. And you see how the arc minutes are written there? It almost looks like how you'd write 60 feet. And then you've got your 60 arc seconds in 1 arc minute, and you can see how that's written. It's almost written like inches. So having 60 minutes in a degree, it's like 60 minutes in an hour, and 60 seconds in a minute. You see the correlation of like time here. So if we were to take 1 degree and work that out to how many arc seconds, there's about 3,600 arc seconds in 1 degree. So like think about the moon, right? If you've got the full moon and that's 0.5 degree, that would be about half of that in arc seconds. So imagine, if you will, if I said, all right, this is how we're going to try to work this. We know that there's 3,600 arc seconds in a degree, and we know that the moon's about 0.5 degree. That means there's 1,800 arc seconds that subtends or goes across the moon. Imagine if you had to split the moon up into 1,800 little pieces. It just gives you an idea of how small and how precise you can start to get with this, and it actually goes a bit further. Long story short, you can navigate the night sky with some crazy precision. So if we had something like, let's say, a dime, a little 10-cent piece, right? And I was going to hold that a mile away. I mean, think about how difficult I would argue impossible to see a dime a mile away. That would subtend 2 arc seconds. So 1 dime, that's small, relative speak. And then you were to hold that a mile away, that's 2 arc seconds. It gives you, again, an idea of just how small of an area of space you can start to get into this. So there's this relationship between angular diameter, or our angular size, and distance. And for some reason, this seems like one of those ones where when kids read through questions, they get confused. But it's a pretty simple concept. Basically, what we're saying is, if things are farther away, they look smaller. And if things are closer, they look bigger. Like if in the day sky, I see an airplane, and I can block it out with a finger, I know that airplane isn't the size of my finger. Or if we see the little picture here, if the individual about ready to get their head squished were to move closer, farther away, it would give the appearance of them changing size. But what it all boils down to is, if something's farther away, it looks a lot smaller. So think about that with like stars, for example. Or why does the moon look bigger than some of these huge, massive stars? Because it's a lot closer, so it looks bigger. Or another way of saying that is, why do those stars look so small? Because they're crazy far away. So your angular diameter, your angular size, could it give you real size? Yes, but you have to know the distance of an object. And we'll spend some time going through these calculations in and of themselves. But right now, I just want you to kind of be aware that you could use this to calculate the size, like physical diameter, the actual size of an object, if you measure the angular diameter, and you can calculate the distance from us to that object. So we're, again, not going to go too much into this calculation here, but I did want to show you how you would calculate the physical diameter. If you take the distance times the tangent of the angular diameter, that will give you the actual size. So how the heck do we know how far away the moon is? I mean, obviously we can't run a tape measure there. Well, the moon's kind of unique in that humans have been there. And I know that there's some conspiracy theories out there that suggest we've never actually been to the moon. But if we haven't, why are there mirrors left behind on the surface of the moon? And my thought is because that was part of the experiments that astronauts wanted to run through NASA, and they left them behind. So yeah, what I'm getting at is there's mirrors on the surface of the moon. You could bounce a laser from Earth to moon and back, and you know that laser traveled at the speed of light, and calculate that out. So does that distance change? Yeah, it's not always the exact same distance from, surface of the Earth to surface of the moon. But you can get pretty darn precise. And then you plug that into our formula here, and you could calculate the size of the moon, the actual physical size, or its physical diameter. How large is it actually? Not just how large does it appear, your angular diameter, your angular size.
And welcome to Brain Stuff. I'm Jonathan Strickland.
And I'm Ben Bolin.
And Ben, I understand we have an interesting question today.
Oh, yeah, this is a good one. All right, so Jonathan, Are you ready?
Yep.
That's not the question.
Okay.
All right. How do astronomers measure distance? How are they able to measure how far away a star is?
Right. So it turns out, that measuring the distance to a star is an interesting problem. So astronomers have come up with 2 different techniques to estimate how far away any given star might be. Now, that first technique involves triangulation or parallax. So the Earth orbits the sun, right?
Yeah.
Well, as it orbits that sun, there's a diameter of orbit of about 186 million miles. So by looking at a star one day and then maybe 6 months later looking at it again, astronomers can see a difference in the viewing angle for that star. So with a little trigonometry, which is frankly terrifying to me, the different angles yield the distance. So this technique works for stars that are about 400 light years away from Earth or closer. Now, there's no direct method currently available to measure the distance to stars that are further than 400 light years from Earth, but there's an approximation, right?
Yes, and this is a pretty clever one. This is the second technique. Astronomers can use brightness to figure out a star's distance. So they do this because it turns out that a star's color spectrum is a good indication of its actual brightness. So like blue, white, etc. The relationship between color and brightness has been proven using the several thousand stars that are close enough to Earth to have their distance measured directly. That would be the 400 light years and closer. So astronomers can look at a distant star, determine its color spectrum, and from the color, then they can determine the star's actual brightness.
By knowing the actual brightness and comparing it to the apparent brightness seen from Earth, that is by looking at how dim the star has actually become. Once its light reaches the Earth, they can determine that the distance of the star is whatever it happens to be.
Right, and there's some other stuff we should probably talk about.
I've got some trivia for you, Ben.
Oh, good, okay.
All right, so let's talk about some of the astronomical units that astronomers use, including the astronomical unit. So the astronomical unit refers to the distance between Earth and the Sun, the average distance. It's about 149 million kilometers or so. Then you've got the light year.
Yeah, what is a light year?
So a light year is it's like a regular year, but with fewer calories. Actually, of course, the light year is the distance that light can travel through the vacuum of space within the span of one Earth year.
So that's pretty big because light's pretty fast.
Yeah, we're talking just under 10 trillion kilometers. That's a pretty long distance. But I've got something that's even longer than that, and that is a parsec.
Hang on, is this a Star Wars reference?
It can be, but all right, so parsec in Star Wars sounds like it's a unit of time. It's actually a unit of distance. And the way it works is you talk about the distance between our sun and some other astronomical object that has a 1 second arc degree difference in parallax angle. Now that essentially means that when we look at the star and we compare it to the sun and we do that again at another point in the Earth's orbit, we get that 1 second arc degree. That distance actually ends up being 3.26 light years. So it's even longer. So there you go. Astronomical units.
Wait, so the Kessel Run?
We'll get to it. Meanwhile, while you guys have enjoyed this video.
All right, so perhaps that got a little bit too much for you. I get it. You know, when you start talking about parsecs and making the calculations of parallax and all that, you know, when you're first exposed to it, it's a little overwhelming. But like anything, you know, if you baby step towards it and practice a bit, it does start to make more and more sense. But if you're at a spot where you at least can kind of trust me that there's ways of making calculations to determine distances to stars and far off objects, we can move forward. So here's some questions for you. And again, just kind of think about the basics of angular diameter and what that means. So that's just going to be how something appears in the sky. So if I said, what would happen to our angular diameter if an object got farther away? In other words, how's an object going to look if it was getting pulled farther and farther away? If somehow I could push the moon farther and farther away, how would it appear? It would be smaller. So what would happen to our angular diameter if the object got closer? Well, if I could pull the moon closer, it would appear bigger. So what would happen to angular diameter if the object somehow shrank? Well, if the moon shrank and got smaller and smaller, it's going to appear smaller. How's about if it got larger? If like a star started to swell, it would look larger. So basically what we can say is distance and angular diameter, they're inversely proportional. In other words, the opposite happens. If one gets bigger, the other gets smaller. And angular diameter and size are proportional. In other words, how big it appears in the size, if it gets bigger, it's going to look bigger. If it gets smaller, it'll look smaller. So which of these graphs is correct? We've got angular diameter by distance. I'll give you 30 seconds to take a look. Okay, so this graph is incorrect. If you look at graph A, it says if your distance is small, the angular diameter is bigger. Or if your distance is far, the angular diameter is smaller, which is what we just said from those questions. How's about these graphs? Now we've got size and angular diameter. Let's take a look at those two. Give you 30 seconds again to determine which is correct. Okay, so this is our graph that's not correct, graph A, and this is our graph that is correct, graph B. So if we look at this, we've got angular diameter is small if the size is small. In other words, if something's small, it looks small. If something's large, it looks large. So one last word here on Earth versus Mars and that distance. I thought maybe looking at how long it takes to get there would be something of interest because we've discussed the moon a little bit, and Mars is hopefully the next location for humans to visit.
When we see all these beautiful images of Mars coming back from the Curiosity rover, it's easy to forget that's another planet. And that planet is really, really far away. So how far away is Mars? The answer to that question changes from moment to moment because Earth and Mars are orbiting the Sun. At times, they're on the same side of the Sun, their closest point, also known as opposition. From our perspective, Mars and the Sun are on opposite sides of the Earth. They're in opposition in our sky. And other times, Mars is on the other side of the Sun at its most distant point, known as conjunction. We see Mars and the Sun in roughly the same spot in the sky. But it gets even more complex than that. Both Earth and Mars follow elliptical orbits around the Sun. When their orbits match up, we can get very close oppositions or very distant conjunctions. In the next opposition of Mars on April 8, 2014, Mars will get as close as 93 million kilometers. But back in 2003, Mars got as close as 56 million kilometers, the closest it had been in thousands of years. And we'll get another close approach in 2018. And so the conjunctions can vary too. The most recent conjunction in April 2013, Mars was 364 million kilometers away from Earth, on the other side of the Sun. And in June 2015, it'll be 384 million kilometers. The vast distance between Earth and Mars has a real impact on our communications to the Red Planet. NASA engineers controlling the Curiosity rover and other spacecraft have to consider the time it takes for signals to reach Mars and then return. When Mars is at its closest point, it only takes about 4 minutes for light to travel to Mars and then another 4 minutes to get back. So if an engineer wants to take a picture of a rock on Mars, it'll take about 8 minutes to see the results of that command. But when Mars is at its most distant point, that round trip takes much longer. A signal from Earth takes 20 minutes to reach Mars and then 20 minutes back. The first person to ever calculate the distance to Mars was the astronomer Giovanni Cassini, famous for his observations of Saturn. Giovanni made observations of Mars in 1672 from Paris, while his colleague Jean Richer made the same observation from Cayenne, French Guiana. They used the parallax method to calculate the distance to Mars with surprising accuracy. However, astronomers now calculate distance to objects in the solar system using the speed of light. They measure the time it takes for signals to reach spacecraft orbiting other planets. They can bounce powerful radar off planets and measure the time it takes for signals to return. This allows them to measure the distance to planets like Mars with incredible accuracy. The distance to Mars is far, really, really far. And yet, Mars and the rest of the planets are right next to us when you consider the vast distances of the cosmos. Thanks for watching. Now make sure you click subscribe on our YouTube channel.
Okie dokie. That concludes the last lecture for Unit 1. As always, you got questions, concerns, feel free to reach out. Till we meet again, take care.